All right, so today we will cover chapter 5, which is on probability. All right, probability is usually people's least favorite chapter. Okay, some people like it, but most students, this is their least favorite chapter. But it's a necessary part to statistics because it forms our reasoning for what we do in the future. But, so we got to get through it. Before I dive into chapter 5, are there questions from chapter 4? The regression, correlation, all of that stuff. All right, settle down, you guys. Okay, we're good. We're good on chapter 4, regression, correlation. Okay. Next week we've got a quiz. You're going to see a question on regression, correlation. I'll show you a scatter plot, a line of best fit with an equation, and I'm going to ask you some questions. Interpretation of the intercept, interpretation of the slope, identifying the correlation, and things like that. All of these things, again, they're detailed on the homework page, just like they were for last week's quiz. Okay. Again, I want you guys to be able to study and prepare and succeed, so I have them listed. This week we're going to cover a lot of probability. There's going to be several questions on probability on next week's quiz. Okay. Again, generally people's least favorite chapter. I'll do my best to kind of explain it and help us understand. But you have to do your part in studying, doing your homework, and practicing. Okay. All right, then we'll go on. So. All right, so probability is our way to kind of describe the chance that something is going to happen. What is the chance that a random event will happen, okay? So what do we mean by a random event? Okay, so in probability and statistics, the word random has a very specific meaning. Okay, today in pop culture, random, the meaning has lost its essential meaning, and it's come to mean like, haha, I'm hilarious or something. I don't know. But random describes the event where the outcome cannot be predicted, okay? An event where the outcome cannot be predicted, but just because it cannot be predicted doesn't mean it cannot be understood, okay? So, random events have outcomes so a very simple and perhaps the most common is if I take a coin and I flip it, the outcome of this coin flip is a random event. So if I were to flip this coin, can anyone predict the outcome of the event?
No.
No, not with any certainty. Okay. But but we can still understand. There's something we can understand about it. Okay. And by that I mean, if I say what is the probability that the coin lands heads, you would tell me
50.
Yeah, 50%, okay, or 0.5. And when we describe probabilities, we leave them as decimals. But percentages and decimals are the same thing. It doesn't matter. Okay, so we could say the probability coin lands heads equals 0.5. Okay, don't say 50-50. Okay. The probability that a coin lands heads is 0.5, okay? 50-50, there's two numbers there. It's not a probability. Probability is just a single number. Okay? The reason why we say 50-50 is because probability that a coin lands heads is 0.5, and the probability that a coin lands tails is 0.5. Okay. Alright, so I'm going to flip this coin. Okay, and it has landed. And let me ask you another question. What is the probability that the coin has landed heads?
0.5.
Now pay attention. What is the probability that the coin has landed heads?
1.5.
Okay, it's a little bit of a trick question, okay? The reason being, the coin has landed. There's no uncertainty about this coin. It has either landed heads or it has landed tails. It does not make sense to ask the question, what is the probability of the coin having landed heads? Because I know what it has landed. You guys don't know. There's some uncertainty on your part. However, the event has happened. So there's no uncertainty, so it doesn't make sense to talk about probability. Okay? It has either landed heads or it has landed tails. So there's no probability that it has landed heads equals 0.5 if we're talking about an event that has already happened. Okay? So probability only makes sense for when there is uncertainty, to speak. So if you wanted to make a statement, you cannot say the probability that the coin has landed heads is 0.5. You can say the confidence, my confidence level that the coin has landed heads is 0.5. You can say I have a 50% confidence that the coin has landed heads. But regarding probability, it only makes sense for events that haven't happened. It landed tails, by the way. So, okay, does that make sense? Okay, so for events for things with no uncertainty, things that are not uncertain, but we do not know the answer, but for which confidence, our confidence level. concepts that we got to talk about, okay? There's theoretic probability. And we have empirical probability. Okay? Theoretic probability, these are usually based on concepts. And math formulas. Okay. We calculate theoretic probabilities kind of by thinking. Okay, we find these. And most of the probabilities that you calculate in this class will be theoretic probabilities, okay? Okay, I'm not sure what's going on back there, but I'm just going to ask you guys to be respectful to the rest of the students who are trying to pay attention and focus. Okay, so just keep the noise level down to a minimum, please. Empirical probabilities. All right, empirical probabilities we find through simulation. Okay, we find by actually, or this is either found through actual data or through simulation, okay? This is useful if the situation is very complicated and the math becomes too crazy. But we're not really going to delve too deep into empirical probability because we're not going to deal with very many situations that are too difficult to find empirically. Okay? I mean, too difficult to find theoretically. So let me, so just a very simple example. Okay, we're going to just use the coin flip example again. All right, so when I said the probability, okay, and I'm going to say that the probability that the coin lands heads is equal to 0.5. So this is shorthand for writing probability that the coin lands heads is 0.5. I'm just writing probability of heads is equal to 0.5. This is an example of a theoretic probability. Okay? We think about a coin, we think about what can happen when you flip a coin, and it can land heads or tails, and we say they have an equal chance of happening, therefore the coin probability that it lands heads is 0.5. Okay, so that's a theoretic probability. what would be an empirical probability? Okay, an empirical probability, and I just lost my coin. Sad day for me. Is to find the empirical probability. What this would require me to do, let me grab another coin. Okay. Is, let's say I've never seen a coin before, or let's say I have no understanding of coins. I have no idea what this 0.5 business is, okay? What I would do, if I've never seen a coin before, what I could do to figure out the empirical probability of a coin flip is I would have to sit here, okay, and I would flip a coin, all right, and it landed tails. Okay. And so after one coin flip, the probability that I have observed of it landing tails is 1 out of 1. Does that make sense? Okay. Let's say I flip it again. All right. Well, that one didn't really flip, but let's say I flip it again. Okay. And then it lands tails again. Okay. So after one coin flip, what I've observed is 1 out of, or I'm sorry. Let's do the probability. I should say the probability of heads. Okay. After one coin flip is out of the one coin flip I've seen heads 0 times out of 1. So my probability of heads so far equals 0. Okay. Let's say I flip the coin again. So this is my first flip, second flip. Let's say I got tails again. All right. So now, what is the probability of heads? 0 out of 2. So my probability of heads after 2 flips is still 0. My third flip. Let's say I get heads. So my empirical probability would be
1 over 2.
1 out of 3, right? I flipped the coin 3 times, and out of those 3 coin flips, it ended up being heads once. So the probability of heads is 1 out of 3.333. Let's say I flip it a 4th time, and I get heads. Okay? So it's 2 out of 4, and the probability of heads is 0.5. And if I flip it a 5th time, and let's say I get heads, we would have 3 heads out of 5 coin flips, and my probability of heads is 0.6. Is this okay with everyone?
Yeah.
Are there any questions on where I'm getting the 0s and the 1s and the 2s or anything like that? Okay. Alright, so the empirical probability is we actually carry out the thing, or we set up some kind of simulation to simulate coin flips. And we don't do it 5 times, but we do it something like 5,000 times, or maybe 500,000 times, or 1,000,000 times, okay? If we're doing simulations, we can do 1,000,000 usually quite easily. If we're doing actual coin flips, we would probably get pretty tired of flipping the coin after a couple hundred. But back when statistics and probability was being studied very early on, they would give prisoners the task of flipping a coin, and they would have to record, thousands and thousands of coin flips because they wanted to understand, is empirical probability really what we think it is, okay? And so maybe after 10,000 coin flips, okay? So maybe after 10,000 coin flips, you have observed 4,981 heads. Okay? So your empirical probability of heads would be what? 4,981 divided by 10,000, and that would be 0.4981. Okay? That is your empirical probability after 10,000 coin flips. so what we notice, okay, and this is actually the rule, is that when you study something and you do the empirical probability, if you do something many, many, many times, the more number of times you do it, okay, that number should be closer to the theoretic probability than if you did it just a few number of times. Okay, this is known as the law of large numbers. We do many simulations or trials, many trials or simulations. The empirical probability should be closer to the theoretic probability than if we did fewer trials. Is this okay? Are there any questions on the difference between theoretic probability and empirical probability? So we understand these. Understand these two. Great. Alright, simulations and random numbers. Sorry, my M and the U kind of ran together, but it's simulations and random numbers. So, let's say we wanted to understand this coin flip thing. And we said, is it really 0.5 or something? Okay. Well, we could sit there and we could flip this coin 1,000 times, 10,000 times, or 1,000,000 times. But it would take a really long time, and we probably don't want to do that. So we might set up a computer simulation to simulate flipping a coin. Okay? In reality, the simulations we run are usually more complicated than flipping a coin. Okay? If we're going to go through the hassle of setting up a computer simulation, it'll probably be more complicated than flipping a coin. But we're going to just stick with this coin flipping thing. Okay? Now, computers, they're going to use random numbers as part of their simulation. Okay? And random numbers are basically the digits 0 through 9. Okay? We're going to use digits 0 to 9. And each digit has an equal chance of appearing. So if you for any single digit, it cannot be predicted. It's a random event. Okay, so just like the coin flip, you cannot predict the outcome. But if you do it many, many, many times, you can understand something. So, just a quick check. If I said, what's the probability that the digit 4 appears? What is your answer here?
1 out of 9.
1 out of 10, exactly. Okay? There's 10 digits, 0 through 9, and each one has an equal chance of appearing, so the probability that the number 4 appears is 1 out of 10, or 0.1. Okay? And that goes the same for any other digit. Okay? So the probability of a 7, also 0.1. Okay? Same for all 10 digits. Yes?
But if the computer's deciding, wouldn't that still make it not random?
Yeah, so there's a whole argument in computer science, okay? And it's technically pseudo-random numbers because computers use algorithms and there's no real random thing going on in a computer. But for all intents and purposes, pseudo-random numbers are pretty darn close to actual random numbers, okay? And depending on your random algorithm that you're using, they can be secure or not secure, whatever. There's different systems that people use, okay? So we're just going to pretend like these are actual random numbers. Okay? So it would be the same as if we wrote the digits 0 through 9 on 10 slips of paper, and we put them in a hat, and we mixed it up, and then we drew out a number. And then we put it back in, we mixed it up, and we drew out the number. Okay? Same idea here. All right, so if we wanted to simulate coin flips, okay? With a coin flip, we only have 2 outcomes, heads and tails. And the probability of heads and the probability of tails is 0.5 each. So how can we map random numbers to our coin flips so that it works? Okay. Well, so if we wanted to simulate a coin flip, okay, we've got to take the random numbers from a computer and turn them into coin flip outcomes. So one possible mapping, okay, one possible setup, and this is not a very good one, but one possible setup is if you see the number 0, we're going to say this is heads. And if you see the number 1, we're going to say this is tails. And if you see anything else, so that would be 2 through 9, we're just going to ignore it. Now, would this work at simulating coin flips?
Yes.
Yes, okay? Because heads has an equal chance of showing up as tails, and these are the only 2 outcomes that our computer is going to simulate, okay? Because everything else it's going to ignore. It's going to just say, so if the computer spits out the number 3, it's going to say, oh, you know what? This is an instance where maybe the coin rolled underneath the couch, and I can't see it, so I got to flip it again. Okay? And it's just like, in this case, the coin rolls under the couch quite a bit. Okay? So that's one possible setup. Not a very good one, but it works. Okay? What might be a better setup? Yeah.
Having half of the numbers be for heads and half of the numbers for tails.
Yeah. So maybe another way to simulate coin flip is so this is better. Is we're going to say if you see the numbers 0, 1, 2, 3, or 4, that's 5 of the numbers. Say you saw heads. And if you see 5, 6, 7, 8, or 9, say that you saw tails. Okay. Here you don't have any wasted numbers. And heads and tails show up with equal probability. So this would be a good way. Okay? Heads and tails. So far, so good? Okay, great. All right, so what if we wanted to simulate rolling a die, okay? Six-sided die. How would we want to do the setup there? So maybe just think about it for a second, just so those who just need a little extra time can think of a satisfactory answer. So if we wanted to simulate rolling a die, okay? With rolling a die, the faces 1 through 6 have an equal chance of showing up. Okay, so what should we do here? What's that?
0 through 11.
0 through 11? What do we do? 0? Okay, but I can't get 0 through 11 because my computer can only do 0 through 9. 0 through 9. So what do I have to do?
0 through
0 through 5.
Okay, I would just say let's use 1 through 6,
1 through 6.
and then we'll ignore 7, 8, 9, and 0. Okay? So basically, 1 goes to 1, 2 goes to 2, so on and so forth, all the way up to 6 goes to 6. And then as for 0, 7, 8, and 9, we will ignore. Okay? Because my computer can only give me 0 through 9. Okay? It cannot give me 10, it cannot give me 11. If I needed 10 and 11 for some reason, okay, simulating something else, I can look at 2 numbers at a time, okay, or I can look at 3 numbers at a time. If I needed more complicated, for more complicated situations, look at 2 or 3 or more digits at a time. Okay. So if I look at 2 digits at a time, how many possible digits sequences can I see? I can see up to 100, okay? Because I can see 0, 0, 0, 1, 0, 2, all the way up to 99. So this is 100 possibilities. Okay? So I just asked the computer for 2 digits at a time, 2 random digits. Okay? Because again, it can only give me 0 through 9, 1 at a time, but I could take 2 at a time, or 3 at a time, so on and so forth. So the digits 0, 0 have an equal chance of showing up as the digits 3, 7, as they do the digits 4, 9, so on and so forth. Alright, is that okay? Alright, you got a few questions in your homework about this stuff. Not too bad. Alright, so let's Alright, so this topic of simulation I just covered very briefly. That's about all we need to get into for simulation in this class, okay? And you got a few questions in the homework. It's not going to be too complicated, alright? I think the questions in the homework might call you to use a random digits table. That's basically, you've asked the computer to give you some random digits, and it just gives you this stream of random numbers, okay? and you're going to use that to kind of carry out the coin flip simulation and stuff. But we're going to spend the bulk of our time talking about theoretic probabilities. Okay? Yeah, the simulations, they can get really complicated. You can take entire courses or series of courses on simulations, okay? And it gets into stuff called Monte Carlo methods. That's basically what a lot of tech companies use to run simulations for customer behavior and things like that. All right, theoretic probabilities. All right, so let's we'll talk about a few ways to find theoretic probabilities. Okay. All right. So our first rule is that any probability. Okay. So there's an important distinction. Okay. Let's say we have an event, random event. Random event A, all right? We will say the probability that A happens is equal, and we're going to write probability of A. Sometimes we also write just P. Okay, so sometimes you see the R, sometimes it's not there. It's not a big deal. Okay. Now, so this is important. We do not say A equals some number. So when we said the coin lands heads, okay, we will write probability that the coin lands heads. Or we might write probability of heads because it's understood that we're talking about the coin landing heads, okay? And so we might write the probability of the coin lands heads is 0.5, or probability of heads is 0.5, okay? This is correct. Okay? Please do not write heads equals 0.5, okay? Heads doesn't equal 0.5. It's the probability of heads is 0.5. Okay. So it's important that we leave this probability, okay, if we're talking about probabilities. Or if you just want to write probability of H equals 0.5, that's fine, okay? But the key is that we keep the probability there. Probabilities will always take on a value between 0 and 1. Between 0 and 1, inclusive. So the probability of A is always going to be between 0 and 1. Okay, that's how we write it symbolically. Here, I'll put this on the top. Okay, if A doesn't happen, so A could happen or might not happen, right? So we call when A doesn't happen, we call that the complement of A, okay? complement with an E, meaning it completes the picture, okay? Because A happening and A not happening, that's the complete set of everything, right? There's only two, for anything that we're talking about, the universe can only contain two possible options. A happens or it doesn't happen. That's it. There's nothing else. So we say the complement because it completes everything, right? So sometimes you will see this as the probability of not A, okay, or the probability of A complement. Okay, this is A does not happen. Right? And the probability that A does not happen is equal to 1 minus the probability of A. So if we're talking about coin flips, if our event is coin lands heads, what is the complement of heads? So the complement of heads is that the coin did not land heads, okay? Which we call the coin landed tails, right? So the complement of heads is the coin lands tails. Is that okay? Yeah, it says event. Okay, but it's an example also. You can write example. Event, coin lands heads. Doesn't matter. Alright. So the probability of heads complement would be equal to what? 1 minus the probability that the coin lands heads. And what is the probability that the coin lands heads? 0.5. So I get 1 minus 0.5. And 1 minus 0.5 is equal to 0.5. So this just confirms what we already knew, that the probability that a coin doesn't land heads is the probability that it lands tails, and that probability is 0.5. Questions? Alright, so let's talk about rolling a die. So here's another example. We roll a die. Alright, when we roll a die, what's the probability that I get a 5 or a 6? What's the probability that I roll a 5 or a 6? Yeah, okay. Alright, so there's 6 possible outcomes. 5 and 6, 5 or 6 account for 2 of those. Okay? So our answer is 2 out of 6 or 1 out of 3. Great. Is that okay?
Yes.
Or 0.33. 0.3333333333. Okay. So what would the complement of this be? What is the complement of rolling a 5 or a 6? No, I'm not asking for what's the probability of the complement. I'm asking what is the complement. So what is the actual event that we're talking about? Yeah, rolling a 1 through a 4. Or rolling anything other than a 5 or a 6. Okay? So the complement, okay, not rolling a 5 or 6, or basically rolling a 1 through 4. Okay. So what is the probability of not 5 or 6? Or 5 or 6 complement. Yeah. So we would write 1 minus this thing, 1 minus 1/3, which You could give me 2/3 or 0.66666, or at some point you'll probably round out to a 7. Okay. Okay. For certain events, if we're talking about events with simple outcomes, okay, finding probabilities is easy. Okay, simple outcomes are where all the outcomes have an equal chance of happening. All outcomes have an equal chance. So, examples of events with simple outcomes: flipping a coin, rolling a die, picking a card out of a deck. Okay? So if you have a situation like this, then the probability for any event of some event is equal to the number of outcomes encompassed by the event divided by all the number of all outcomes. Okay. All right.
Yes.
So the example is rolling a 5 or a 6. Okay, that was an event of a simple outcome. Okay, all the die rolls have an equal chance of happening. So if we're talking about 5 or 6, the number of outcomes encompassed by the event, there are 2. Rolling a 5, rolling a 6. 2 outcomes out of the number of all simple outcomes, of which there are 6, the numbers 1 through 6. And so that's how we got 2 out of 6, or 1 out of 3. Alright, so rolling a 5 or 6. Probability of 5 or 6 is 2 out of 6, or 0.33. Okay. That's how we did that. Alright. Are you guys familiar with a deck of cards?
Yes.
Okay. Most of you are. Some of you are not. Okay. How many cards total do we have? 52. How many suits? 4 suits. And the numbers are what? Ace through king, right? Or basically 1 through 13, okay? Ace through king. Alright, so what if I ask, what is the probability of selecting a face card? Okay, so a face card is Jack, Queen, and King, okay? Some people count aces as face cards, but there's no face on an ace, so they are not technically a face card. High value card. Okay, you want aces if you're playing poker. Okay, face card, Jack, Queen, or King. There's a Jack, Queen, or King for each of the 4 suits. So what is the probability of drawing a face card? 12 out of 52. Okay? There's 12 face cards out of 52 cards total. Okay? So we have the Jack, Queen, King hearts, diamonds, clovers, and spades. So you have 12 face cards. 52 cards total. There you go. Simple outcomes. So events with simple outcomes. So this only works for that. Is there a question?
What is the last symbol after the
A spade, a spade.
Oh.
It looks more like, I don't know, something like this.
Oh, okay.
Oh, that's good. Good job.
Alright, we'll take a break at 8 o'clock. Okay, so I have a question. What if I asked you, okay, now we are going to roll 2 dice. Alright? So if you go to Las Vegas, what's the game where you roll 2 dice? Craps, okay. So I don't know if anybody here has played craps.
Yes.
Okay. Alright. Now, when you first start, you win if you roll a 7, okay? But if you roll anything other than a 7, then it goes into play, and then you're trying to roll all the numbers except for 7, okay? What is the probability of rolling a 7? How can we figure this out? Okay, if you roll 2 dice, what is the probability of rolling a 7? Now, how do we go about calculating this?
12.
Okay.
2 12.
All right. So how many outcomes total do we have? Is this an example of simple outcomes or not, or what? What are we dealing with here?
Empirical simple outcome.
Okay, we're going to use theoretical probabilities here, so we're not going to do any kind of simulation, so not empirical. Okay. What is the probability of rolling a 7? Okay, theoretical probabilities. Okay, do we have simple outcomes? What are the outcomes when rolling 2 dice? The probability of rolling a 7, meaning the 2 dice add up to 7, okay? All right. What are the possible outcomes when we roll 2 dice?
36.
Okay, there's 36 possible outcomes. Now, I want to distinguish this, okay? Because someone might incorrectly say, so this is wrong, okay? It would be incorrect to say the outcomes, this is true, the outcomes are rolling a 2, 3, 4, all the way up to getting a 12. That's true. Those are the possible outcomes in terms of the number, the sum of the dice that you can get. Okay, that is true. However, these are not simple outcomes. Okay. They are not simple outcomes. Ever play Monopoly? How often do you roll a 12?
130.
Not very often, okay? 1 out of 36 is the theoretic outcome, okay? How often do you roll, a 6, 7, or 8? A lot more than rolling a 12. Okay? So these are not simple outcomes. So it would be wrong to say that one of these is 7, and there's a total of 11 possible outcomes. Okay? So it would be wrong to use, 1 is a 7 out of 11 possible totals. So the probability of 7 is equal to 1 out of 11.0909. So that would be wrong, because this assumes simple outcomes. We do, however, we can have simple outcomes if we look at all 36 possible outcomes. Okay? There are, on the other hand, there are 36 possible simple outcomes. Is this okay? Alright, and that is, so just imagine the dice are different colored. You got a red die and a blue die. Okay? On the red die, you can roll a 1, 2, 3, 4, 5, or 6.
What is that word? Simple outcomes, what?
Simple outcomes?
And then on the bottom.
Blue.
Okay.
A blue die. Okay? And you can roll a 1, 2, 3, 4, 5, or 6 on the blue die. Okay, sorry for the mess. Alright? Okay, and then so we can add up all of these numbers. If you roll a 1 on the red and a 1 on the blue, your total is a 2. And then it goes 3, 4, 5, 6, 7. Alright. So watch me write a whole bunch of numbers here. Okay. Those are all 36 possible outcomes that you could get. Is this okay? Somehow maybe I should double line this to distinguish this from the totals. A red die and a blue die. Alright, you don't have to copy this chart too late. Okay, so how many ways can we roll the 7 then? There are 6 ways. I could roll the 6-1, the 5-2, the 4-3, the 3-4, the 2-5, and the 1-6. Okay? The 6-1 is different from the 1-6. Is that okay? Rolling a 6 and then a 1, 6 on the red die and a 1 on the blue die, is different from rolling a 1 on the red die and a 6 on the blue die. Can we accept that? All right. So we roll. There are 6 possible ways to roll a 7 out of 36 possible die rolls. Okay. So the probability of rolling a 7 is 6 out of 36. 6 ways to roll a 7. 36 possible outcomes. So if you go to Vegas and you play craps, you could say, I think the next die roll is going to be a 7. Okay? Now what's the probability that it's going to be a 7? Yeah, 6 out of 36 or 1 out of 6. Okay? So if you say, I think the next die roll is going to be a 7, you will be right 1 out of 6 times, overall in the long run. Okay? And if you say, I believe it's going to be 1 out of 6, it's going to be a 7 on the next die roll, and you bet $10, and you win, how much is Vegas gonna pay you?
$10.
Okay, if you play the pass line, they'll pay you $10.
Yeah.
But if you play the 7, they'll pay you $50. Okay, it's 5-1 on the actual 7. Okay, so they're treating it as a 1 out of 5. Okay, and that's how they're taking their cut. Okay, why don't we take a short break? All right, come back at we'll say 8:05, so we'll take a 10-minute break.